Evening, everybody. 5 o'clock on Tuesday night. Finally, we're back in class. We had the extra week of break. So first off, everybody able to hear me? Okay, you can just put it in chat if you're not. Okay, it's always a good start. I figure it's been a couple weeks, technological issues. Let's double check and make sure everything's working. Thanks for the feedback, guys. All right. Briefly, let's just talk about where we're at. So, you know, when we parted ways before break, we did the midterm and the take-home problems. That's all been graded, uploaded, and more. Now we're going on to the next module, which as you guys saw in the lesson, we're moving on to integration now. And obviously, just like with Calc 1, there's differentiation in integration. It's going to be similar here. We're going to focus more on integral multivariable calculus. A couple things I want to mention. Number one, obviously, we had the extra week of spring break, which did move our end date back 1 week. That's up to you. You know, this is a course, because all the materials are available, you can finish early, meaning you can still finish at the regular time that was expected, which I think was like May 13th. Totally fine. But the final has been moved back to May 20th to kind of coincide with our schedule. And so I'm just going to go with the regular 8 weeks as it was going to be done, had it started a week ago. For those of you guys who want to work ahead, that is totally fine. I kept the dates for the take-home problems the same, even though I moved the schedule back for people who decide to work ahead. The other thing I want to mention, the final is not cumulative. All right. It's going to pretty much focus on what we do from here through the end of the semester. Now, obviously, some of the concepts from the first half of the semester are going to be present in the stuff we're doing, but it's going to, the final will be over modules 4 and 5. Okay. So I just wanted to let you know that stuff, and I'll bring that up again as we go on. But now I want to kind of dive into the material. As you saw, we switched from differentiation to integration. And so we're looking at definite integrals of multivariable functions, or what are called iterated integrals. So 14.1, I'm not going to spend a lot of time talking about. Really, in these first two sections, there are two things that we need to get over. And both of them are more on the procedural side. Number one is, how do we take the antiderivative of a multivariable function? It's very similar to taking the derivative. You think of one variable as constant, integrate with respect to the other variable. All right. So that's one thing. The other thing is setting up the limits. All right. So that's going to be where I focus most of our time today. I'm going to talk about a couple other things about what a definite double integral gives us. But then, I'm going to move on to 14.2 and talk about the region of integration, because that's usually the bigger sticking part. And because we're going to be heading into triple integrals pretty soon, we want to get this idea of a region in the XY plane down, because that's going to get extended. All right. So let's dive right in. If you recall from Calc 1, we had our fundamental theorem of calculus. Our definite integral was equal to our Riemann sum with an infinite amount of intervals. Obviously, once that becomes infinite, what happens is our intervals become infinitely small, and that's what allows us to continuously calculate that value of the function. So same basic idea in multivariable, But as you can see, the Riemann sum's a little messier because now we have Riemann sums in two directions, one in the X direction and one in the Y direction. Guys, we're not gonna spend a lot of time calculating Riemann sums of multivariable functions. They're messy. You guys have done that in Calc 1 and you did it again in Calc 2 with numerical integration. I just bring this up because it does follow the same definition as a single variable integral. So what we do is we sum up the volume of m times n rectangular solids. All right. If you remember what happened with Riemann sums in Calc 1, we summed up the area to get our estimate. We take the limit as n goes to infinity to get the exact value. Same idea here. So what we have is what we call the definite integral and an iterated integral, meaning we're taking it more than once. Okay. So let's just talk a little bit about what the iterated integral gives us. We're not going to worry about these two. We're not going to do that today. But here's the first one that you want to take because it's so closely related to what we did in Calc 1. And that's that the double integral gives the volume under our surface. So if our surface is defined by F, then the double integral gives us the volume underneath F inside the region R. Okay. If you remember back to Calc 1, the definite integral gave us the area under the curve between our limits. Now it's giving us the volume because we've got this third dimension. So that's going to be a way we talk about it pretty often in here with a double integral. We'll move into some context later, but today I want to focus on calculating them. Now, and this is going to be useful in setting up limits. If you set your function to be 1, well, then all we're really doing then is calculating the area of our region. Now, the reason I say that this is really useful is because when you go to set up your limits and your limits are defined by functions, which is something we're going to look at in 14.2, really all you're doing is very similar to the area between two curves that you did in either Calc 1 or Calc 2 whenever you saw that. And I'll be very explicit about that when we get to it. But I think that thinking about it that way helps in setting up the limits for your region, which, like I said, I think is one of the hardest parts about definite integrals is actually setting them up. Calculating them, it can take a little while depending on the limits, but it's not too bad. The last thing I'm going to mention in this section is the double integral, just like in Calc 1, can give us the average value of a function. So in Calc 1, in single variable, basically you did your average value by dividing by the length of your interval. So in Calc 1, the average value of our function, this should look familiar, was 1 over b minus a times the integral from a to b of f of x dx. So you divide it by the length of the interval to get the average value of your function. In multivariable, you divide by the area of the region. All right. Now, again, these are some interpretations and some of the things we can do with the double integral. So far, we haven't really dealt with how you calculate one, which we'll do here. I'm going to do a few examples here in a little bit, but I want to talk a little bit about 14.2. Before I go into 14.2, any questions so far? Okay, now let's talk about setting these things up so that they can be calculated. And then, like I said, I'm going to give you guys some to practice, because that's the biggest thing in these first couple of sections is just A, switching from derivatives to integrals, and B, How do we handle integration in multivariable calculus? Okay. So our function's continuous over some region. This is the definition we looked at last time. Nothing new. So what we do is we basically do the first integral, and then we'll do the second, the inner and then the outer. And we'll talk about order today as well, because that's going to be something new that we haven't had to deal with in the past. So how do we decide that? Well, let's talk about some of our cases. Our first case is our most basic case, and that is if our region is just some rectangle. So X is in between two constants and Y is in between two constants. This is a very easy case as far as setting up the integral, because then the order doesn't matter. All right. So if we're doing the double integral of F, then we could do from A to B and do in terms of X first, and then C to D and then do in terms of Y first. All right. Now, so far, we haven't even really given motivation for why the order might matter. And that's because we haven't gotten on a non-rectangular region. That's when it really starts to get interesting. So if we have a rectangular region, the order doesn't matter. So for instance, if this is our function here and we got to set up our region, it doesn't matter which one we do first. We could do the X direction first, 0 to 3 of 10 minus X minus 2Y. Now we're doing X first, so I do dx here. And then we're going to go 0 to 2 in the Y direction. And there's our iterated integral. Yeah, this one's not a bad one. We'll go ahead and do it for a little bit of practice. So first thing you do, oops, we need a dy in there, excuse me. So first thing we do is we do the inside integral first, which means we're integrating with respect to X. So what does that look like? Well, we're going to have this integral symbol out front. So 0 to 2. And I'm going to take the integral of each of these with respect to X. 10x minus x squared over 2 minus, now here you got to be careful. This is a constant in terms of X. So that would be 2yx. All right. Now that's going to go from 0 to 3. And then we'll still have to do our integral with respect to y. Now, before you do the integral with respect to y, you got to finish off your fundamental theorem, which involves putting your limits in. So we put in our 3 and then we'll put in our 0. Now, for notes purposes, I'm going to put them all in. So we have 10 times 3 minus 3 squared over 2 minus 2y times 3. And then our fundamental theorem of calculus says I plug in the lower limit. Now this one's all going to zero out. Again, this is more for notes purposes. And I don't want you to forget to plug in both limits. That lower limit won't always be 0 and it won't always zero everything out. Next thing you'll do is you'll simplify as much as you possibly can. We want it to be as easy as possible when we go to do the antiderivative in terms of y. So we're going to have 30 minus 9 halves minus 6y dy. And we could take the antiderivative now, but I'm going to combine these two constants so that I don't have to deal with them. Like I said, I like to simplify as much as possible. So 0 to 2, 30 is basically 60 halves. So 60 halves minus 9 halves gives us 51 halves minus 6y dy. Now this should, we always have to do this by hand. Do you always have to do them by hand? Absolutely not. Obviously, when you're doing the homework, you can use technology. When you do get to the proctored part of the exam, you're going to have a few that you're going to have to do by hand. So you do need to make sure you know how to do antiderivatives by hand. But no, not always. Like I said, setting it up is the biggest part. So I completely encourage you to use technology to make sure you have it set up correctly. And by the time you get to your last step, we should be into a single variable calculus problem. This is something you guys all could have solved without ever having ever taken this class, right? This is going to be, what do we got? 51 halves y minus 3y squared. And our limits are 0 to 2. The 0 will 0 out. So we're going to have 51 halves times 2 minus 3 times 2 squared. The whole second part's going to be 0. So let's put that in there for notes. So we end up with 51 minus 12 or 39. So that's how procedurally we do a double integral. Questions at this point? Again, I could have done this in the complete opposite order. I could have gone from 0 to 2 and integrated with respect to y first, and then x. Would have gotten the exact same thing. Okay. Order did not matter at all on this one. All right. So let's talk about when the order matters. So if all of our limits are constants, or if our region is a rectangle, all the limits are constants, order doesn't matter. Now, case number 2 is if the top and the bottom of our region are defined by functions. In this case, the order does matter. The reason it matters is because eventually we want to get to a number. Well, if our upper and lower region are given in terms of x, and we integrate with respect to x first and then with respect to y, we won't have an opportunity to integrate out the x. All right, we want our final answer to not have any, to be able to sub for our variables. So because our region has upper and lower boundaries that are not constant, that tells us that we want to integrate with respect to y first. Now, remember I said this is kind of like doing area between curves. So here's where I make that analogy a little bit more clear. Remember I said earlier in 14.1 that if our function, if our integrand is just 1, all we're really doing is calculating the area. So if this is a to b, g of x to h of x of just 1, dy dx, let's look at what's going to happen. So my first thing I'm going to do is I'm going to take that first antiderivative, so a to b, and that's just going to be y from g to h dx. So upper minus lower. So a to b of h of x minus g of x dx. Well, think about what we know about this integral. This does the area between h and g from a to b. So I know it's been a while since you guys have done this, but if you can remember back to doing area between curves, it was top minus bottom from a to b. That's where these limits are coming from. So identifying your limits is the same as identifying the top and bottom for area between curves. All right, so that's one way of thinking about it that I think can be helpful in setting this up. All right, and again, what you're going to look for And I'll show you a couple different examples of this to kind of give you a better feel for it. But is your top just defined by a single function? Is your bottom just defined by a single function? All right. Now we could have something similar where the left and the right are defined by single functions. In this case, we'd want to do X first because we want to go from left to right and then bottom to top, or left to right. Left to right, bottom to top. And just like area between curves, we would do right minus left. So that's going to be our upper limit. That's going to be our lower limit. And we would do X first. Okay. So these are going to be the more interesting cases, and we're going to spend a little bit of time on this now, on setting them up. I might calculate one more just for good measure, but I want to spend more time on setting a couple of these up so that you can see that. Okay, because again, I think that's the trickiest part of the double integrals is when you have a region that is not just four constants. How do you decide lower limit, upper limit? So that's what we want to make sure we focus on. So notice that we had to switch the order of integration depending on our limits. So we need to pay attention to that. Some limits can be written in either order, and it doesn't matter. In some cases it does. All right, so I'm going to show you a few examples of where our order matters, okay? Or doesn't. All right, so let's say we had this integral here. Now, I'm not going to do the whole thing on this one. I'm just going to go through the setting it up. All right, so we've got a rectangular region. And one thing we're going to need to do, so since this is not rectangular, triangular, which means one or more of our limits have to be defined by a function. So we need to give it a function for this guy right here. So what do we have? We have a y-intercept of 3. It's going down 3 and over 5, so a slope of -3/5. So y equals -3/5 x plus 3 would be the equation of that line. All right. So, and it's invertible, which is great. You know, we might do it the other way, but let's do it this way first. Now, the next thing you do with your region, we want to see if there's a definite top and bottom. So the top is our curve, the bottom is the x-axis. Or is there a definite left and right? Well, the left is the y-axis, the right is our curve. So this is one where that can be done in either order, and I'm going to set it up in both orders. We won't have time to calculate it today because I just want to give you guys some time to try some, but I want you to see what I mean by this one can be done in either order. We'll look at one later that can't, and I'll show you why. Well, I can, but it's harder, and I'll show you why. All right, so let's say we're going to do so the reason the order doesn't matter is because if I look left to right, I've got a single boundary for the left. I've got a single boundary for the right. If I look top to bottom, I've got a single boundary for the bottom, a single boundary for the top. So I can go from bottom to top, left to right, or I can go left to right, bottom to top, without having to break up my integral. All right, I'll show you one where that isn't so straightforward here in a little bit. It has nothing to do with the lines being squiggly. All right, guys, I'm going to give me a little bit. I'm going to give you an example, but I want to get through this one first, and then I'll show you when it does matter. It doesn't have to do with the lines being squiggly. It has to do with how many different functions defined our top, bottom, left, right. But I want to set this one up so that, and then we'll go on to the next one. Okay. So let's say we're going to do let's say we're going to integrate in terms of X first. So we're going to go, so we're going to go left to right. Actually, no, sorry, I have it set up to go top to bottom first. So let's say we're going to go from top to bottom, and then we're going to go from 0 to 5 in the X direction. All right. So we're going to do Y first because we're going to go vertically first. So when I go to set up my integral, my lower limit on Y is 0. My upper limit on Y is this curve here. So negative 3/5 X plus 3. And then we put in our integrand, which is 5 plus X plus 2Y. And we're doing dy first. All right. Now there's a couple things I want to point out. There's one thing I want to point out before I go on. Notice my limit is in terms of X, and I'm integrating in terms of Y first. We never want these two things to match, because if I were integrating with respect to X first, then I'd be plugging in this limit. So I'd integrate with respect to X, get the X's out of there, but then I'd be putting an X back in as part of the limit. Okay. So that's why if I'm integrating with respect to Y first, my limits can only be in terms of X, or vice versa. If you're integrating in terms of X first, your limits can only be in terms of Y. Now your outside limits, they have to be X. They must be constants. They cannot be in terms of either variable. And we can see that X goes from 0 to 5. So that would be a setup for this integral that would calculate this function over this region. All right. Now, another thing I want to point out, because sometimes this question comes up at this point, it might come up later. Now, we know that a triangle is half of a rectangle. So you may be wondering if we could do the rectangle and then cut it in half. The problem is there's no guarantee that the function is symmetric over the rectangle. So we can't just do that. We have to treat this region as its own region, not just half of the rectangular region. Okay, now let's talk about doing it the other way. So now we're going to go left to right, bottom to top. So we're going to do dx first. So 5 plus x plus 2y. We've decided to do dx first. That means our limits need to be in terms of y. So that means I have to go back to my function. And I've got to write this in terms of y. So I need to solve it for x. So solving for x, subtract 3 off of both sides, right? Y minus 3. And then multiply both sides by a negative 5/3. We can put that in our mx plus b form if we want. Minus 5/3 y. And then a negative 5/3 times a negative 3 gives a plus 5, which makes sense. We've got a y-intercept of 5. So because this region was invertible and made either the top or side, whichever way we looked at it, we can do this one either way. And now we can go from 0 out to that curve. So 0 to the minus 5/3 y plus 5. And then y is going to go from 0 to 3. All right. Either of those will both give us the same answer. And, these can take a little while to do by hand, as you saw. I fully encourage you guys to use check technology to check your answer. I want you to do a couple by hand because we do need to be able to do integrals. But I realize when you're working on the homework, you're doing a lot of them. And if you have it set up wrong and to go through the problem, it can be really frustrating. So please use Wolfram Alpha, Symbolab, things like that to help you. They can both do double integrals. Okay. Robbie, I want to get back to your question because it is a good one. So, you know, how did I know that the order didn't matter? Well, in this case, not only was it triangular, but it was a right triangle. So let me show you a region where the order does matter. All right, so this is one from the 14.2 worksheet. So let me throw this in there so you guys can look at it. So I'll put it in chat here. So, oh, I got to get rid of that writing. Actually, we'll write around it. We're not going to let it bother us right now. Or maybe it'll be in the way. Nope. Okay. So I'm going to look at 2D. The region is 2. Actually, yes, I do need to get rid of that. Get rid of this writing here. So the region is y equals 2 minus x and y squared equals x. All right. Guys, one of the things you're going to want to do is plot your region either by hand or using a plotting program. All right. So what does this look like plotted? So what I did is I went ahead and solved it for x so I could plot it. So here's the plot of our region. All right. Now, let's go back to talking about order. All right. Now, if I want to do top bottom first, notice that the top bottom here is different than the top bottom here. That doesn't make it undoable. What that does mean is I need to split it into 2 integrals, basically right here. And I would have to do one double integral for this part and one double integral for this part. Is that a bad thing? Not really. But obviously having 2 integrals makes more room for error. So if we can do it as a single integral, we like to do it that way. There are going to be some that can't be done in one order. It's hard for me to come up with a whole bunch of examples, but I just want to really push home what I'm talking about the top, bottom, left, right. Now, if I look at this from left to right, I see I've got a clear curve here on the left, and it's y squared. And I've got a clear curve here on the right, and it's 2 minus y. So if I'm going to do this one, and let me change colors just so you know that I'm doing this one now. You know, I'm going to have my function in there. I'm not worried about the function right now. And I'm going to go left to right first. So I'm going to do dx first. That means I need my limits in terms of y. My lower limit is the left. So y squared. My upper limit is the right. So 2 minus y. Notice I'm integrating with respect to x, so those limits have a y in them. Next, we're going to do y. Now that means we need these intersection points. Now, yes, I can actually put the cursor over there and get the intersection points. So I got 4, -2, and 1, 1. But let's say we had to find them. To find where 2 curves intersect, you set them equal to each other. All right. And so we subtract, let's see, we add a y to both sides. So we got y squared plus y minus 2 equals 0. Quadratic formula, or these will factor into y plus 2, y minus 1. And we get y equals -2 and 1, which corresponds with what we're seeing graphically. And we wanted limits for y. Notice, remember, these are points. Make sure that, you know, we're going bottom to top. So we're using the y value of these points. So -2 to 1. All right. So that would be to do it as a single integral. Again, we could do it the other order, but we do have to split it into 2. And then our top and bottom would be -square root of y, +square root of y here. Here it would be negative square root of y up to this curve. It's very doable, but it does get a little bit more cumbersome as far as all the work we have to do. Did that help with what I mean by choosing the order left, right, top, bottom? Does that help make that a little bit clearer? Or are there still questions about that? That didn't help. Okay. So what questions do you have then?
So last night I was doing the homework assignment for this, and I had like pretty much a problem just like the one you're looking at right now.
Sure.
And I don't remember the exact numbers that I had, but let's go with like 1 and 0. And I had like 0 first and then 1.
Okay.
And it said it was wrong. And I like went back through all my work and I was pretty sure that it was all correct. And then I thought like maybe to try -1, and then that still didn't work, but then I like flipped the order of my numbers and then that worked. But I don't understand how or why.
Yeah, without looking at your region, it's hard to say. The one thing that is, the one thing that's consistent is, we either go left, right, and then bottom, top, or vice versa, bottom, top, left, right. We'd have to take a look at your region because every region is going to be a little different, and that's where it's going to take a little bit of practice. Now, if flipping the limits is all you did to get the right answer, then one set might have been backwards initially. Again, it's hard to say without looking at your problem, but this is something that's going to take a little bit of practice for you guys if you haven't done it before. Like I said, I think the best thing to do is to look at them as area between curves. How would I calculate the area between these two curves? I would do right minus left. Okay, then this curve is my upper limit on the inside integral. This curve is my lower limit on the inside integral. And then I will use these intersection points to get my constants for the outer limits. Okay. Questions at this point? And it's okay to not have this down perfectly. You guys are just learning it for the first time. I'm going to show you guys. I want to show you guys one more thing, and then I'm going to let you guys work on some problems, and then I think that may produce some more questions for us. All right, one last thing I want to look at. And it goes along with this order idea, and this can be interesting. So sometimes we switch the limits of integration in order to calculate an integral. For example, this integral here. This is not a trivial integral to do in terms of x. So what we want to do is switch our limits of integration. Well, that means we do need to know what the region looks like. Okay. So what this is telling us is that dx, so x is in between those two. So x is in between e to the y and e, and y is in between 0 and 1. Now, it may not be real obvious what the graph of x equals e to the y looks like. If you're not sure, use something to help you out. You know, we can, this is something we can do in Wolfram. So plot x equals e to the y. So it looks like e to the x, but notice they're putting the x on the vertical axis, so they're not really helping us out. I don't really like that plot. So e to the y, I don't like the way that came out, but this is the same thing. If we solved for the inverse, y equals ln of x. So that's essentially the plot that we're looking at. All right. So if we were to graph this, e to the y, change colors of our graphs. That's the graph of x equals e to the y. Now, we also have a limit at x equals e, which would be about right here. Well, when x equals e, y equals 1. That's this point here. So that's the point e comma 1. All right. So here's our region of integration. So this is kind of like our triangle. Notice there's a left and a right, which is the way this one was done. Or we could do it from top to bottom. Now, again, we can do this because this part of our region was invertible. So I need the inverse of it, which as we saw is the function y equals ln of x. So instead of doing dx first, I'm going to go from 0 to ln of x over ln of x dy. Now we're going to go in terms of x. X goes out from here to here. Well, this part we know is e. Oops, that's our upper limit. Here, well, this is where the y is 0. So that's the point 1, 0, because natural log of 1 is 0. So our lower limit, sorry, that kind of looks like a 0. Let me clean that up a little. So our lower limit is going to be 1. And that's our dx. Now, the reason we did this is so we could calculate it, because now doing the integral with respect to y, well, this is all a constant. So when I do that inside integral, I get just x ln of x over ln of x times y. And then we'll have to put in our limits 0 to ln of y. And then we'll do dx. So when I put in that natural log, look at what happens. It actually simplifies. Oops, how did that become a y? Sorry, guys. Made a little error there. This should have been an x. When that gets plugged in, our lower limit's 0, which is going to 0 everything out. Those actually cancel. And now we get a basic integral, x squared over 2 from 1 to e. So e squared over 2 minus 1 squared over 2. Or if you want, e squared minus 1 all over 2. So there are going to be some cases where switching the order of integration is actually to our advantage. Now, don't worry, I'm not going to expect you to come up with that. Yes. So for this problem, we switched the order because it made the integral easier to do. That's not going to be something I'm going to expect you to come up with right off the bat. In fact, if I give you something like this, it'll say in the problem, switch the order of integration, then calculate the integral. Okay, because we could throw this into Wolfram Alpha or Symbolab, and it'll probably come up with an answer for us. What we're doing is trying to see if we can calculate some of these by hand. So what you do in this case is you draw out your region, find the inverse of your boundary, and then you can switch the order. All right, so sometimes we switch the order because it's to our advantage when we can. There are going to be some where switching the orders not something we want to do, which was the case that I was showing you where it has to be split into two integrals. But what I want you guys to practice today is A, doing a double integral, B, setting up your limits of integration given a region, and C, if we have enough time, I don't know if we'll have enough time for 3 problems, but I'm going to give you 3. C would be doing one of these where you switch the limit of integration to make the integral easier to do. Okay. Questions at this point? Okay. And what we're going to do is let's do, let's see. Let's do, excuse me, 3 groups today. And I'll put this in again once you guys are in groups. But these are going to be the problems that you are working on, okay? All right. All right, guys, welcome back. Great job in your groups. I know it's been a couple weeks since we've done that, so I appreciate it. So it's okay if you didn't finish all 3 problems, because we're going to have some more time to work on 14.2 on Thursday, because we're only going to have 1 section for Thursday. And that's going to be how a lot of this second half of the semester goes. I'll go through 2 sections on Tuesday and only 1 section on Thursday. You'll probably only get through 1 section in groups on Tuesday and then the other 2 on Thursday. So as far as posting in the forum, go ahead and post your solutions for 14.1, but don't worry about 14.2. I'll put you in the same groups on Thursday so that you have time to work on 14.2 if you didn't get a chance to try those, and also the problem from 14.3. All right, and that'll be how most of our sessions go, because as always, I want to give you guys time to work on some problems to see what kind of questions that produces. Okay, at this point, we got a couple minutes left. Any questions?
Just to reiterate, you said that the final exam won't be cumulative. It'll just be from this section onward.
Correct.
Okay.
Yeah, and I mean, just to remind you, obviously you're going to be doing partial derivatives and some of that stuff within the topics that we're going to be doing the second half of class. But yeah, the exam is not going to be cumulative in that, I'm not going to be asking you to do the cross product or some of those questions that you saw in the first, on the midterm. It's going to be focused and based off of what we do from here on out. So, you'll be allowed two more note cards, and you can make those completely from scratch. So it'll have all the same setup as the midterm.
Thank you.
Yeah, no problem. Other questions? So we have taken our initial dive into iterated integrals, which is going to get us started for this second half of the semester. Like I said, I think 14.1, 14.2 are good sections to build a base on. So 14.2, where you're having to look at that region, decide the order of integration. That's something you're going to want to practice in the homework. And by all means, guys, feel free to use technology on some of those to calculate the integral, just like I told you on 14.2, number 2, because as you're trying to learn how to set up the limits, you don't want to spend a bunch of time calculating the integral by hand too, because if it's set up wrong, obviously the answer is going to be wrong. So I want you in 14.2 to be more focused on setting up the limits of integration. 14.1 is a good section for you to practice the actual process of doing it by hand. Okay. Because I just don't want you to get stuck on some of those problems and have them take you a really long time because it's set up wrong to begin with. Okay, so take advantage of things like Wolfram Alpha and Symbolab. Okay, so it's 6:31, so we're a minute over. If you guys don't have any questions, I'll see you on Thursday. So 14.3 will be the online lesson for Thursday. I'll talk a little bit about 14.3. And then we'll go into groups. And if you want, you can work on finish 14.2 or the 14.3 problem, whatever your group wants to work on. All right. Don't forget to post 14.1 sometime before 5 p.m. on Thursday. All right. All right, guys, have a good night. And I will see you on Thursday. And as always, guys, in between now and then, you got the forum. You can email me questions. Tutoring is back up and running. So things are back into pretty much full swing for us. No problem, guys.